Hi everybody. So in this tutorial I'm going to backtrack a little bit to the first tutorial and fill in some information that wasn't on the original tutorial, and then I'm going to move forward to look at other example problem situations. We're going to derive equations, and then hopefully if there's time I can start some example problems that I eventually want you to try on your own. The only way you're going to really find out how you get this. So we defined gravitational potential energy, UG, as negative GMM over R squared. And I believe in the other tutorial we solved for what that value is for a 1 kilogram object on the Earth. But what I didn't do, and I had since added since I made a tutorial, is another definition, something called gravitational potential. And I know this is going to be confusing to you, but we'll work through it. So gravitational potential is just that. It's just potential. It's not potential energy. And you're saying, well, they sound like the same thing. Why are we splitting hairs here? Well, we want to, because this gravitational potential is a more convenient number to look at. So gravitational potential is V, whereas potential energy is U. We're going to see something similar when we get into electrical potential energy and electric potential. Electric potential is called voltage, so you can almost call this gravitational voltage, but I'm just going to keep calling it potential for now. It's not a big deal right now, but I want to point it out because it's going to come up again. So long story short, is gravitational potential V is defined as, whoops, I don't want to put an equation near just yet. Whoops, dropped my pen. As energy or potential energy per unit mass. Okay, it's kind of like an energy density of sorts. Okay, so by definition, equation-wise, V sub g is nothing more than UG divided by whatever mass I bring into a field. So let me kind of, before I expand this, let me give you a better context. Let's say I have some planet of big M, and I'm in a certain spot in that field. Let's say this far away, R. Now, that's not very helpful. Okay, let me redraw that. So we are a certain distance away from the center now, remember. We're distance R, and we have a mass of a planet, and we have a little m there. So this little m feels a potential energy. But we want to quantify the potential by being at this spot right there, regardless of whether we have a big mass or a small mass. And that's what gravitational potential does, V. So by definition, V is whatever energy exists between these two divided by this mass. And so what if I take this equation and put in the UG equation, which is right here, and simplify, I end up with negative G M, excuse me, big M, all over R. Whoops, this should not have been an R squared. I keep doing that. So what this tells us is how much energy per unit kilogram we have at that spot. So let me do an example. If we look at VG for the Earth, okay, I'm going to do it the long way. I'm going to say it's negative G M all over R. So if I plug in the mass of the Earth and negative G, right, so negative 6.67, I won't put the 7 there, but it's there, times 10 to the 11th, 6.0 times 10 to the 24. Oh, yeah. Just pretend that's 6 times 10 to the 24, and divide it by 5.96 times 10 to the 6. Okay, so let me punch it into the calculator. Okay, so what I'll have is negative 6.7 times 10 to the 7th joules per kilogram. So if I bring in, let's say, 1 kilogram, then I could say my potential energy, I know I've already done this calculation in the previous one, but here's an alternative way. I can say my potential energy is equal to my gravitational potential times the mass that I bring there. And so that would simply make it 6.7 times 10 to the 8th joules. And I hope that's a number, I should say negative. And so what that tells us is by having this V value, I can interchange any mass I want to conveniently get the energy. Okay, so let's move on now. We've already done the escape velocity, so let's turn to another important application of this modified version of gravitational potential energy, and that's looking at orbits. So let's say we have something in orbit. So we have some generic planet going around the sun. Okay, we can look at the total energy of that orbit and reveal something important about it. So that's what we want to do, ultimately, is there, and we're going to do this in stages. Hopefully you will understand each stage, because this involves review of circular motion, which is a good thing, and then the important outcome of that. So we want to find the total energy, sigma E, of a planet by virtue of being in orbit. And so it has that energy by virtue of moving, so there's kinetic, and it has gravitational potential because it's in a well, because it's trapped by the sun, it is bound to the sun, so it has potential. Now we're going to pretend we have a circular orbit, but I'll talk about an elliptical orbit and the implications of that as well. Okay, so we want to express the kinetic energy not as 1/2 mv squared, but in terms of its distance. So we want to come up with a way of finding its orbital velocity and relating it to the forces acting on it. We've done that before. That we did in the universal gravitational chapter coupled with circular motion. So let's review. So when you're in orbit and moving in a circle, you have a supply force. What's that supply force? Of course, it's gravity. And what's our equation? G mm over r squared. There's a demand on that force. What's that demand on the force? Well, that's mv squared all over r. We're going to do it in terms of v and rather than period, so it's a little bit easier. We're not going to go for Kepler's law here. Okay, so we're going to set them equal to each other and solve for v. Well, we've done that before, so basically g mm over r squared equals mv squared over r. We see the little m cancels out, so the mass of the planet doesn't matter. This m is the sun, and one of the r's cancels out. So what does that leave us? And if I take the square root of both sides, we see that v orbital is radical g m over r. Okay, so if I want to calculate the kinetic energy a planet has, I can use 1/2 mv squared. So that's going to be 1/2 mv orbital squared. Now I'm just going to put in my new equation for v orbital, and I have 1/2 m, and then this whole radical thing squared is g m over r. And if I combine that, I get 1/2 g mm over r. That kind of looks familiar. So there is one way. That's always going to be the equation for the kinetic energy of an object in orbit. Always. So you can either remember that, but you should be able to derive it based on this to this to that. Okay, now we want to find the total energy. That's just the kinetic. What's the gravitational? Well, we already know what the gravitational is. The gravitational is always going to be negative g mm over r. Okay, based on how far away the planet is and the mass of the sun and the planet. So now we can combine them, and I'm going to do the algebra here, and then I'll put it in the box. So we're going to take this, add it to it, well, let me do this. The sum of the energy, total energy, is negative g mm over r plus what we got from there, and that's 1/2 g mm over r. I should make my m's different, but I think you get the idea. And so I have g mm over r in both terms. This has a positive half. This is -1. So -1 plus 1/2 is -1/2. So it's nothing more than negative g mm over r to r. Okay, or 1/2. Now, this is important. That negative value is telling us something critical. Okay? So note that the value, the total energy, is negative. What does a negative total energy means? It indicates that we have a stable orbit. Okay, hold on a second. Okay, I'm sorry. A closed orbit. In other words, it's bound. The planet is bound to it. It can't escape because its energy is negative. If you want it to escape, remember, to escape, not be bound. If we want to not be bound to escape, we want our total energy to be greater than or equal to 0. Okay? So if you have any negative energy, that means you are in orbit or you are bound to that, either on the surface or, again, circling around and around. Now, what is in all orbits? What then is the ratio of potential to the total? Well, if our potential is negative g mm over r, and we divide it by g mm over 2r, or that, we see that that's 2. So you always have, your potential energy is always going to be twice that of your total energy. Okay, so if we want that planet to escape, and that's just as well could be a rocket, then it's got to get a kinetic energy that is twice its original value. So I mentioned something about what happens in an ellipse, okay, because that's truly what our planets are. So this is an exaggerated ellipse, and what that means is, as we get closer, right, our gravitational potential gets less. It becomes more negative because of the 1 over g, the proportion where ug is proportional to negative 1 over r. So as r gets smaller, this becomes a more negative number. So if the potential gets more negative, which means it goes down, that means the kinetic goes up. So in other words, the planet is in a sense falling in a little bit, so it goes faster. So it's consistent with the idea that when you're closer to the sun, the speed is faster, and then as we move further away, the orbital speed goes down because our potential is going up. It's approaching 0. So keep that in mind. That's a simple little conceptual question. Okay, I have about 3.5 minutes left. Let's see if I can start one of the example problems. Okay, so let's say we have a space shuttle. It has a certain mass m, and it is launched in the direction of the Earth's south pole. It has a kinetic energy given by the following expression. So note that it's not in terms of 1/2 mv squared, but rather based on the derivation we did before, because this is going to make it a lot easier. So we want to know, show that this shuttle cannot escape. How do you know that? We want a negative total energy. Okay, that's what you want to show, that the total energy of that space shuttle is negative. So how do we do that? Well, we want to calculate the total energy. And the total energy is the sum of its gravitational potential. Remember, if it's near the surface of the Earth, it has gravitational potential, plus whatever kinetic we give it by launching the rockets or the rocket boosters. This equation is always the same thing, negative g mm over r. In this case, this is the Earth's radius, because that's how far away we are. And then we're going to add to it the kinetic that we got from the launch, which is 7/8 g mm over re. So when you look at it like this, turns out to be a pretty simple problem. You just got to understand this is the connect key to figuring out. So I notice I got a gmm over re in both terms. This is -1 here, 7/8 there. So that's a -1/8 gmm over re, and there we can see the negative total energy means that that space shuttle, while it might be able to go into orbit, or it might be able to go higher than an orbital distance, it cannot escape the Earth. If we turn off the rockets, it will eventually come back down or stay in orbit, depending on the trajectory it takes. All right, now it enters a circular orbit of r around the Earth. Show that the total energy is this. We already did that. So I want you to go back, maybe pause it and see if you can do this on your own without looking back at the problem I solved before. I think it's a really good exercise for you to do, try on your own, where you know what the answer is, and if you get a little bit mixed up, you can go back and change it. So I'm going to go on in 3. It says use your expression for EKA and your answer to B1. Well, B1 is already given. We don't have to, you're going to derive it, to show where exactly, how high does the space shuttle go. Okay, so in other words, we're launching it, we know it's not going to escape. So basically, the idea of how high it's going to go is just like if we launch something up in the air. We look at our total energy to begin with, so our energy at the beginning is going to equal same amount of energy at the end. It's just going to shift. So we already showed our total energy in the beginning is -1/8 gmm over re. So that's going to equal, okay, our new energy, which is going to be in the form of gravitational potential. And I'm sorry, let me step back for a second. Okay, so our total at the beginning is the sum of the potential kinetic, and we already saw in 1b that that's got to equal the total orbital energy, which is -g mm over 2r. So what I'm solving for here is r, where this is the r of the E. So if I do the algebra, I see all the g's and the m's cancel out, and I end up with basically